So hi everybody, we continue to the next question, which is about a submarine, like we did in the previous, but a little easier question. So we have this nice submarine, right? Here it is. Have some propeller here, right? Nice windows to see the sea, and we define that this is, in these questions, gonna be our x direction. Let's see that, yeah, our x direction. This is z, and this is y. And we said that the wall of the submarine is infinitely big. It's a huge wall compared to some fish that is around here somewhere. And we also have this oscilloscope, right? And we said that the submarine have a positive charge. In the previous question that we deal with the submarine, the charge was pretty complicated. But now, let's keep it simple. We want to talk more about potential, not about charge, and not about Gauss's law. So the potential gonna be right now constant. Okay, to make stuff easy. Okay, perfect. And the first thing I wanted to ask you is just to do a small refreshment about refresh about Gauss's law. So the first one is going to be what is the electric field inside the submarine wall. So how are we gonna do it? We're gonna use Gauss's law, right? Gauss's law. So this is the wall of the submarine. Here I have my axis, right? This is z, this is x. So Gauss's law said that the total charge, that the geometry, let's do it like this, that the geometry, the geometry of some closed area, right, A, of E dot dA must be equal to what? To the total charge inside this A. So it's Q in A divided by epsilon 0. So we're gonna choose this box, right, to be our volume. Let's give it a three-dimensional look, right? This is the box that I choose, and the wall, this is the wall which is infinite. Continue in this direction how much that I want, right? And I want to know what is the electric field in some location x, right? Let's do in some location x around here, right? This is the point x, some random location inside. I just give you a brief reminder. This is d, this is the thickness of the wall. And from the axis, it's actually d over 2, just to remind you. So if you're gonna do the box, you see this box, so I can calculate what is the charge inside the box. What is it? It's actually this distance, right? It's actually the volume of the box. It's integral, right, of dq, and we know that this dq is actually rho 0, which is a constant, multiplied by dx, dy, dz, and we can take this rho outside of the integral because it's constant, and we can get rho 0 over epsilon 0 multiplied by what? This integral is actually the volume of this cavity, of this area that I decided of. So what is the volume of it? It's actually 2r, which is this distance. I decided to call it 2r. The height is h, and the width is w. You see it? So it's 2r hw. It's a volume of a box. Perfect. We got this term. Everything is good. Now let's deal with the electrical field inside this shape. So the electrical field here is actually, I can divide this integral into two parts. The first one is the front one, right? I have two of these kinds of surfaces. Let's do it integral of boxes to here, which is E at location X, plus or minus, it doesn't matter, plus or minus. Actually, let's do it R, because we decide that the box is at length R, right? And I have two of those, here and there. And I have this dA, plus I have this one, right? I have 4 terms of long part of the box, right? Which is have here 2L, and here it's or H or W. It depends if this or this, right? E at some many locations dot D. dA, and we talked about it, that all the direction of the dAs in these parts, in this and in this, are with the x-axis, also the electric field. So the cosines between them is 1, and the cosines between them is actually 0, because these parts, see, have dA which is perpendicular, see it, to the direction of the electric field, so this dies out. So we have only this. We can take E outside of the integral because E is a constant in this location, right? So here it is. So actually we can delete this part. That's right. That this part is equal to. I don't want to waste a lot of time on this part because you saw it in the previous tutorial. So right now I want to focus on the potential. So I need to write this term. This one can go outside, so we got 2 E at the location specific R, right? Multiplied by the area of this part of the box, which is HW. And we can see that HW cancel out, the 2 cancel out, and we find what is the electrical field. The electrical field is actually a linear function with the radius, with the distance, right? So depending on the size of the box that I want, I can always set the electrical field is some constant, you see H, multiply by R. You see it? So as you go from here, the electrical field is getting stronger and stronger. That's what happened here. See it? Here it is. This is the wall. This is the wall. Right? So if you're here in the middle, if you go far away, the electrical field getting stronger and stronger and stronger. Okay? Remember this one? Perfect. And now the professor, there's some professor here in the submarine that want to investigate the phenomena, the voltage phenomena, the potential phenomena in the sea. And he decided, like we did in physics 2, to call the region potential 0. For example, if you have some problem in physics 1, you decide that the floor is actually at height 0. You can decide it whatever you want. It's relative to the other stuff. So it's important to remember if this is 0, it's affect the other stuff. If it's not 0, the same. So it's a relative term. So let's write down what is decided to do. Okay, I leave this part. And it's important to say that this is in, which means inside the wall. So what the professor actually said, he said that the potential at 0, 0 is equal to 0. And what is the general term of the potential? So let's remind you from the lecture that the potential, different potential, is equal to phi final minus phi I, right? And this one equal to minus integral from the initial point to the final point of the electric field dot dr, the direction that I want to go. Okay? So this is the term, and he said to us that the location is 0, so if we can change this I to I equal to location 0, right? So that this is 0 and this is 0, right? So we can write the term that the difference in potential that phi f is actually equal to minus from location 0 to some location R, E dot, and we know that this dr is actually to go away from the submarine, is actually going in the x direction, so we can call it dx for simplicity, and the dot between this one x and this vector is actually the magnitude multiplication. We can do it like this. So we find the definition for the potential in every location, right? This is true for every location. And the question I want to ask you is, what is the potential inside the wall? So now what we're actually going to do, we're going to use this term and put it inside here to understand what is the potential inside the wall. We know what is the electric field, and we know what is the direction we want to go. So this is pretty clear. So let's do it. So phi f, let's do phi in. Phi in, which means phi inside the wall, the potential inside the wall, is minus, don't forget this minus, 0 till some location R, is equal to the integral on this, R0, H0, epsilon, multiply by R, oh, here it is, perfect, multiply by R, okay, if we change this to X, we're actually talking about location X. So this one, let's leave it as R, so it will be clear. No, okay, I'm gonna make it clear. Okay, so this was the R, okay, and the R is actually direction. We're going in direction dx in the x direction. Here the distance R is just the size that I decide to call the box. So I can also call it x. Okay, so if I want to use more convenient parameter, I can just use these two. So let's change this to x. Okay, x, and here it's dx. So what is the result that I'm getting? If I do the integral, this becomes square. This is a constant. It could go outside. This also a general x place, right? And so we got rho 0, h0, epsilon 0, x squared over 2, right? And we put 0 and x, so x it stays, so phi in is actually equal to this rho fs hfs epsilon 0 x squared over 2. That's what we got. And don't forget that we have this minus all the time, okay? The exam gonna be an American question kind of like, multiple choice. So you can always fall in these questions because you didn't notice to the minus sign. So don't forget to take this into account. Perfect. And the next question is gonna be, what is the potential outside of the wall? Okay, right now we calculate the potential inside of the wall. So what is the potential outside? So let's delete this. And to calculate the potential outside of the wall, right? We found E. We already found E in. Right now we need to find E out, right? So the question is, so like this, what is phi out? Phi out. And for that we actually need to find what is E out. Because we cannot do the integral to solve this if we don't know what is E out. Perfect. So how we can find E out? We can again use Gauss's law to do right now a box that is bigger than the wall, which is gonna contain all the charge that I have here, which is, this is, Q epsilon 0, Q in A, integral E dot dA, right? So the whole charge inside is rho 0 multiplied by the size of the wall, right? So this is equal to, let's give you the solution. So this is rho 0 multiplied by D WH, right? This is the thickness of the wall, this is the width, this is the height of the box, divided by epsilon 0. And this term is it's like the previous before, it's 2, because I have only these two which are not die out due to the cosines, right? So this is 2, and this is 2, HWE in the specific location X, specific location of the end of my box. So HW, and I get a constant value, which we talked in the previous tutorial, which makes sense because if we talked about some infinite wall, it's something that I expect to have. So we actually found E out. This is the value for E out. Let's do here out. So just a small reminder, we had E in, we have E, a general term in X, which split in two different areas. I have out, what's happening outside, ED over 2 epsilon 0, and this is out of the wall, right? And inside, we had a linear correlation, which was rho 0 epsilon 0 multiplied by Al, right? That's the value that we had before. So we have these two terms of the electric field. And now we actually want to find what is the potential outside as well. So what is the term for the potential? So we said before that the term for the potential was that phi in some location is equal to minus integral from 0 to the specific location on the electric field dr. We said that it can be right as E magnitude dx. It's okay because we know the direction of dl, which is x, and we know the direction of E, which is also x. And if you're going to go to the minus side, right? So it's going to be minus x, and also E going to be going the minus x. So it's always the multiplication of the cosines inside is always positive. So in the same direction. The angle between this and this is always 0. So it's 1, the magnitude of the cosines. Perfect. So right now I want to do the integral, but I have a problem. If I want to go outside, here it is. Want to go outside, so I'm finding some electric field here, and here I find another electric field, right? This is in, and this is out. So which one am I going to choose, right? For this question, because I start my journey where? Here, at 0. So the solution for that is that we can split the integral. We can say that the integral is from 0 to d over 2. What is d over 2? Is this place. This is d over 2. If d is the total length of the wall, so d over 2. And we can use this term, the inside term. Let's do it in purple. And let's put aside the summary. So this is rho 0 Al divided by epsilon 0. This is not Al, x, and here also x, sorry about that. Okay, the x plus, and here I have a minus, so here I can put also at the minus. From where? From d over 2 until the specific location, some out location, right? And from here outside I have a constant value, which is rho FSD, put it in purple also, which is rho, here's dx, which is rho 0d to epsilon 0, perfect, dx. So this is a constant, this is some linear, right? So I'm going to give you the final solution for this term. So the final solution, if I'm going to solve all of this, is going to be minus d rho 0, d can go outside, rho can go outside, to epsilon 0, and inside I have this x out, the location that I'm interested to know what is the potential, x out, right? Minus d divided by 4. Okay? So this is the solution to that question. And the last part is actually drawing our solution. So this is phi out. And remember that phi in, what was phi in? Phi in was minus 0 r in squared divided by epsilon 0 over 2. So the last part of the question is drew the potential function. The potential is a function of x. Okay, so if this is the submarine wall, right? This is the submarine wall. Here is my axis, right? X and the z direction, and y pop to your eyes, right? So what is the potential actually? So we saw that at the beginning, what is this function? Is a said parable, right? So this is gonna be until the wall. I expect to have some parabola, right? This is this one. And then what I'm gonna have, let's put it here x. It's the same. This happens in every section of the question. So, and what is this? This is a linear, right? With a negative slope here, right? The direction here, and we didn't solve this part of the question, but it's the same. The negative side, it's the same. It's a symmetry. The electrical field is going to point that way. The dA and dr are going to point that way, so it's going to be the same. Nothing changed here, so I expect to have a mirror. I can solve half of the question. So this is the drawer, and this is perfect. And now we're going to continue to the next question. I just put here, this is function dot of z of phi of x. Okay, perfect. Let's go to the next question.